Okay, everyone, good morning. This is Jack Van Horn from the University of Southern California and the BD2K Training Coordinating Center, and I'd like to welcome you all to our next installment of the Big Data to Knowledge BD2K Guide to the Fundamentals of Data Science. This is our Section 3 on computing and computing technologies, and I am very, very pleased to introduce Umit Catalyurek, who's Professor and Associate Chair at the Georgia Institute of Technology. He is a professor in the School of Computational Science and Engineering there at Georgia Tech. He received his Ph.D. in 2000 from Bilkent University, and he is the recipient of an NSF CAREER Award, a number of other grants, and the primary investigator on several key awards from the Department of Energy, the National Institutes of Health, and the National Science Foundation. He serves as an associate editor for the journal Parallel Computing and is an editorial board member for IEEE Transactions on Parallel and Distributed Computing and the Journal of Parallel and Distributed Computing. He was the founding general chair of the first ACM International Health Informatics Symposium in 2010. He served as program chair for several other ACM and IEEE related activities. His main research interests are in parallel computing, combinatorial scientific computing, and biomedical informatics. His lecture today is going to be entitled Modern Computing, Cloud Distributed and High Performance, and this is going to be a lecture with a sort of a crash course on computer architecture, high performance computing, and parallel computation. And he's going to be very briefly discussing how to classify computer architectures, how to help make your code parallelizable without too much technical detail, as I understand, but how you may do this and achieve the best performance on different architectures. And before we begin, let me remind you that you can text in your questions using the question submission system here in our GoToWebinar. And please do that, and then at the end, I will ask those questions of Umit at the end on your behalf. Without further ado, Umit, thank you so much. We're very much looking forward to your presentation.
Thank you very much, Jack, for this humbling introduction. As Jack mentioned, right now I'm at Georgia Institute of Technology, but I was at Ohio State for 15 years at the Department of Biomedical Informatics. I was one of the founding faculty members to start the department. And just before I moved here, I was one of the co-directors of MIDA's multi-modeling integrative data analytics training program there. So I am always motivated with biomedical applications. I'm a computer scientist at heart. So this talk will be, as Jack mentioned, from the more computational perspective. And I will try to give you a brief introduction, a very quick crash course on computer architecture in general, high-performance computing architecture. I need to provide some background information so that we are all on the same page. Then I will focus on three, I will say, golden rules that when you're making your application faster on high-performance computing environment or today's computing environment. And I will give some simple examples there, and I will finish up with one application that shows many of those techniques together combined. So let's start with high-performance computing. What do we really mean by high-performance computing? It's one of those terms that there's really no agreed upon terminology. One can say that there's no such thing as low-performance computing, so all of the computing has to be high performance. Why one want to compute anything slow? You want to compute everything fast, which I couldn't agree more. Couple definitions from a couple different places. I don't want to read all of these, but what I want to point out that many of those definitions really tells that aggregating computing power to solve bigger problem, and it talks about a need for high bandwidth, enhanced network, and high computing capabilities. But the definition I would like to use is something a little bit simpler. I just want to use available computing platforms to run my applications quickly, and I want to do this very efficiently. So that, for me, that's what high-performance computing is. It doesn't always mean supercomputing, but I'll come to that in a minute. So why do we care about speed? Clearly, there are many reasons, and there is no point on belaboring the point. We don't want science to wait for computing. We want to compute fast so that we can make the scientific advancement faster. But what I would like to emphasize is we really need to care about efficiency in computing. So when we make computation efficient, that means if we can leverage the computational resources much better, that means there will be more resources available to all of us. So we can do more computation, so efficiency is important. One thing that's always sometimes overlooked is also someone has to pay the bills. So if you're doing a computation, say in a cloud computing environment, if you only care about getting it fast, and if you're using thousands of processors, you're going to pay 4,000 processors. But if you can do it efficiently on less number of processors, that will be also very fast as well. So I can prove that, but I don't really have time to do this. So I just want to emphasize that whenever you're looking for application, as much as you want it to run it fast, you really want to be efficient as well. So supercomputing is definitely HPC, but in my definition, HPC doesn't just mean supercomputing. We will look at some supercomputers. Not all of us will have access to those kind of supercomputers, but I want to tell you a few things about high-performance computing and architecture so that you can use in whatever the environment you have. So let me start with computing today. So I'm going to argue that computing today really means parallel computing, and you need to do high-performance computing. Why is that? Well, first of all, any computer you touch today has parallel processing power. And I will start with a very simple example. Your laptop probably has at least 2 cores. Inside the CPU, it has 2 cores that can do 2 things at the same time. And even more, even your cell phone will have 4 to 8 cores today. So that means that any computer you'll see will have multiple processing power elements. So it's there, so we have to use them. The second rationale is, well, this is BD2K seminar. We're talking about big data and science, and hence the computational data need is really big. We really need to solve some problems that today you cannot fit into your whatever your local computer, your desktop computer is. So some examples are clearly includes genomic applications. For example, metagenomics is one case. If you want to solve a metagenomics problem, you will not be able to run most likely in your laptop. You will need some machine that has much bigger memory. And the other thing is, in some cases, you may fit into your computer, but it may be taking too long. So we don't really have time to do this. So that's why we need to take into account parallelism, and we need to make it efficient. So basically, three reasons. One is, well, it's there. All the computation resources today has parallelism. So if you're not using them, you're wasting those resources. The second is your problem doesn't fit in your small computer, so you have to do it parallel. The third is it takes too long, and then you want to do it fast. And just to show the tsunami of the data, I mean, these are some slides that you have probably have seen a few times already. Just sequences and whole genome sequencing data in GenBank is really exponentially growing, and we have more than petabyte of data, and we are getting some technologies like Oxford Nanopore, which are small and will make the even generation of the data much faster. So now I want to switch gear and go into a little bit computer architecture. So this is a chart of performance of a single processors over the time, starting from early 1978 to 2012 or so, but the trend is very similar after this point. What I want to highlight here is, if you're doing science between mid-80s and 2003, If you want to make your code faster, all you have to do is just wait. If you wait 18 months, you'll get a faster processor, almost twice as fast, and your code will run fast. But around 2003, we actually hit a few technological barriers that computer architects had to change the way that we produce processors, and this is where we start having multi-core processors. From that point on, if you want to get your code faster, you cannot just rely on time and simple technology advancements that will make your existing sequential code run fast. You really have to think about parallelism. One thing I really want to highlight here, when we talk about speed or measuring the performance of the program, we usually use two terms, bandwidth and latency, or throughput or response time, similarly means the same thing. The bandwidth is the total work done in a given time. So if you're, for example, doing sequence mapping, you have input reads, how many of those reads you can map in a second? This is your bandwidth. The latency is the time between start and completion of the event. So in that case, the latency of a mapping a single read is the time it takes really finding that in the whole genome, pointing that location. As you can guess from these problem description, increasing bandwidth or throughput is much easier, actually. You can throw more resources and you can get to higher bandwidth or higher throughput, but reducing the latency, getting faster response time is not that easy. And you will see that in computer architecture as well. If you plot the relative latency improvement over the bandwidth improvement against the bandwidth improvement, you will see that all of the computer technology, including processors, network disk, the bandwidth really improved much higher than latency. What does it mean? We're really adding more type of resources so that you really need to take advantage of those parallelism in your code to be able to make it fast. So, okay, now I'm going to talk about really computer architectures, and I'm going to use Flynn's taxonomy on how we classify the computer architectures. In one axis, we are looking at how many instructions we can run at any point in time, and we'll just classify them as I can run a single instruction, or I can run multiple instructions at any point in time. And on the other axis, we'll look at the data. How many data elements I can process at any time? It will be either single or multiple. So on the upper left corner is single instruction, single data corner, which is your sequential computer. So basically, you can process one data at any given time. There are alternative architectures where you can actually process multiple data elements, but operate do the same instruction. Let me just show them as pictorially. So this is your single instruction, single data, basically your standard CPU. So you have input data coming, and your processor is doing one instruction at a time and producing the outputs. That's your basic sequential code. Alternative way of you have to do a repetitive task that you can actually do the same. You will do the same processing in multiple elements. Instead of doing them one by one, you can process them in chunks, in blocks. These are also called vector machines, and today actually GPUs more or less falls into this category. So these are single instruction, multiple data machines. So what's the difference between these two architectures? On the left side, showing a GPU, and on the right is a CPU. Basically, CPUs are designed. Current CPUs are designed for optimize for latency. So they operate in single core of the CPU operates on single data elements, and it's really designed to give fast response to single problem. On the other side, GPUs are really optimized for throughput. So where the difference comes from, in the chip design, actually, what makes chip more complicated is the control flow. If you want your chip to do different things, the control flow becomes more complicated. So GPUs takes advantage of that and have a single control unit, but multiple arithmetic units that they can do the operation. So with that, they can produce a higher throughput, and they can actually be more energy efficient with that as well. So, but if you come to today's world, we actually have architectures which have multiple processors operating on different data elements, and they can be actually in different forms. One of them is the shared memory view of the architecture. We used to call them SMPs, symmetric multiprocessors. In that case, you have multiple processors. They can all access to single memory, same memory, but they can do independent work. This will be your workstation with multi-cores or multi-processors in it. Then we can go one step further. We can have processors connect through a network. This will be gigabit network or much faster networks like InfiniBand. In that case, each processor will have a local direct access to its memory, but if they need to do something together, they need to communicate over network. And of course, we can have the hybrid model that there are multiple processors, or today is actually we have the really sorry for the typo, heterogeneous computers, which you have different types of processing units in each computing node, and they are connected through a network. So let me just very quickly go over supercomputers. This is an HPC lecture, so I need to talk about supercomputers. So I'm going to start with a code attributed to Seymour Cray of the Cray computers. If you were plowing a field, which would you rather use, 2 strong oxen or 1024 chickens? So as you can see, this comes from a computer scientist. It doesn't say 1,000, it says 1024 chickens. And the answer to this question is not that easy, actually. It really depends what you want to do. If you don't want to need to plow really deep, and if you have a good mechanism to control those chickens, you can actually plow larger fields with 1,024 chickens, right? But if you need to plow deep, you really need to use 2 strong oxen. And today's supercomputers are composed of different architectures that are mixture of these 2 dilemmas. So on one side, you have very powerful processing elements. They are connected to each other with fast networks. On the other side, you have computing elements that are not that powerful by themselves, like a single computing element in a GPU, maybe, but as a combined together, they are much more powerful. Top 500 is a website that lists world's fastest supercomputers that are known to us. And there might be, of course, other computers that we are not aware of. These are basically ranked by some application, some linear algebra solution to some linear algebra problem. So there are people argue that this is not a good representation of all the application portfolio, but nevertheless, this is one of the list. And what I want to show here is just look at the number of cores column here. Today we're talking about 10 million cores. So if you want to really get high performance on such a supercomputer, really need to think about massively parallelizing your computation. At the bottom, you can see a chart that's plotted from the beginning of the top 500 list, is about 1993 today, and one shows the number one in this list. As you can see, we are reaching about 100 petaflops, and the goal to reach the exaflops is it was about 2000. Initial goal was 2018. Now we're pushing about 2021, and we are making progress in that. What I want you to look at, take for example one of the horizontal lines here. Let's say 10 teraflops. Number one machine was about in 2001, 2002 was in 10 teraflops, and in 2008 the bottom of the list, just 6 years after, had that power. So about 6 to 8 years, number one machine becomes number 500. And if you actually add another 6 to 10 years, 6 to 8 to 6 to 10 years, that number 500 machine power, you will have it in your desktop. So between about 14, 15 years, you may have a computer that was as fast as world's fastest computer 15 years ago. Another thing that I want to highlight is number one is really clearly separate from the rest. If you look at the sum of power, the difference between number one and sum and number one and number 500, number one is closer to the sum. So really, this is a top-heavy list. So very quickly, I don't want to go too much detail. This is the progress of type of the architectures we have. Initially, there were single processors that were fastest machines, but if you just look at this decade, you will see that it's basically two types of computers. Basically, one is clusters that are built on commodity hardware, similar to most of your workstations. They are just connected with some a little bit faster network, InfiniBand and variants. Or there are some, about 20%, really designed as supercomputers like IBM Blue Gene or the top number one machine in our current architecture. Chip technology is also, we will see that commodity hardwares are becoming more prevalent. What I want to highlight here is, as I said earlier, since 2003, we are using mostly multi-core architectures, but starting from 2010, so beginning of this decade, you will see what I call attack of many cores. So those are GPUs, Intel Xeon Phis, or those kind of accelerators that have really those 1024 chicken type of processors, the SAMD processors, which by themselves they are not individually they are not powerful, but combined together they become much more powerful. And as you can see, almost 1/5 of the top 500 machines have those architectures. So now I want to change the topic. So I give you a brief overview of what the processors look like, how they are really composed, and what the current supercomputers look like. And now I want to look at from the application perspective. So let's say that you have an application and you want to speed up that application. When I talk about application, I will use the term workflow interchangeably. So there was another talk 2 weeks ago. Romy actually explained the workflows wonderfully. So the workflows were at the higher level, but here what I'm talking about, a workflow is an application itself. So we will look at parts of the workflow and we'll try to figure out how we can make your application, your workflow faster. The first thing that I will say, and those three rules actually, they are really, if you look at them, are common sense rules, but we tend to overlook them. So I want to emphasize a little bit. So I have some equations in this slide, but just ignore the equations at the top for the time being, just look at the bottom. So let's say that the one on the left, the bars, blue and green bars, shows my application. Let's say that I notice that on the green part is something that's I'm doing repetitively and I can do much faster. Or it's running on one processor that I can actually get a faster processor for that. And let's say that I'm improving that and I'm getting what's viewed on the right-hand side. So the question is, what's the speed up I can get? So you can play with the arithmetic at the top, and you will see that the new execution time is, of course, the blue parts which I haven't improved, they will stay, and I'm just improving the green part, and whatever the improvement is there, that will actually be limiting factor for my speed up. Actually, another way of saying this, let's say that I have infinite resources and I improve that green part so that it's practically zero. Then the maximum speed up is 1 divided by 1 minus the fraction that I improved, which is that parenthesis says whatever left is in the blue. So what does it mean? Let's say that you have a sequence analysis pipeline and you have one slow step, so you call it slow, and it does error correction, for example, of the input reads. So you want to do it fast, and someone says that, hey, there's a CPU that's 10 times faster to do those kind of things, and that sounds very appealing. You want to definitely use it. But when you look at the application, you realize that application is actually I/O bound, meaning that it's reading and writing the file 60% of time. Only 40% of time is really doing that computation. So if you just plug the numbers here, what you will see that your speed up will be is 1.56. So we were talking about a CPU that's 10 times faster, right? We are really attracted with those numbers because they are big, but we lost the perspective that this will actually only give us 1.6 time speed up. So another application that we have done in my group a long time ago, actually, is multiple sequence alignment. So this is a combinatorial problem. Finding the optimum solution, optimum in the sense of computational, not biological, because in the computers we have to have a function to define the optimality, and using that, if we actually use an optimal algorithm which will basically enumerate all possible solutions, even with a small number of sequences, this may take hours, and if you add a few more sequences, this may take years, right? Some of the problems will be intractable, so we cannot solve them optimally, but we have good algorithms, heuristic algorithms, which will solve them in a faster time, and ClustalW was one of them. So I'm not going to go into details of the algorithm, but what I want to say is algorithm basically have three phases: pairwise alignment, a guide tree computation, and progressive alignment. And when we actually look at the execution time of the algorithm, if you look at the chart on the top left, we noticed that pairwise alignment was really taking quite a bit of time depending on how many sequences you have. And when you increase the sequences, guide tree also becoming taking too much time. But for most of our application case, it was about 400. So it was taking more than 90% of the time. So we thought it's great. We make that part parallel. And as we did. So if you look at the chart on the right bottom, so the green line shows the ideal speed up you can get with P processors. If you have drawing P processors, what you expect, your computation get P times faster. And as you can see, pairwise alignment phase of the algorithm, actually, we did get almost linear speed up. That's fantastic. But again, going back to Amdahl's law, plugging this into the equation and looking at in total, what was our speed up, you will see that the speed up was just 3 using 8 processors. So just again to emphasize this a little bit more. So this is just plot of if your 10% of your code is sequential that you cannot parallelize. What's the maximum speed up you can get? And on the x-axis, I have from 0 to 8,000 processors. And you don't see that line because underneath of all of them, and as you can see, it's really actually less than 10. If you look at the best line I plotted here, it says if you have 1/10 of a 1%, so 1,000th of your program was sequential, so you can't parallelize that part, but you parallelize all of the rest, that's the speed up you will get. As you can see, you get pretty decent speed up to 1,000 or so, but after that it starts flattening out, and even if you throw 8,000 processors, you only get 900 speed up, right? So you're practically wasting 7,000 processors at this point. So this is one thing you really need to pay attention when you want to make your codes faster. So another thing that I would say that you need to pay attention is pay attention to locality. So like many years, our computers are composed of memory hierarchies such that lower in the hierarchy has a larger space, but their speed is slower. So from CPU to cache to memory to disk, as you go down, you will get a larger and larger space, but access time becomes really much slower and slower. So what this tells us really, if you can structure your computation such that it actually fits into memory at the upper levels, you will actually speed up your computation really, really fast. So you really need to pay attention to this and at least think about how you can reorder the computation such that you can keep the data most of the time in memory or most of the time in cache if you can actually do that. Another point in the pay attention to locality is in some applications, this was basically a visualization application we have done again quite a bit time ago. You may have the data actually in distributed settings. So you may have, your collaborator may have been, for example, generating some data. In this particular case, we're looking at different acquisition models for image modalities, and you want to create an visualization that integrates all of this data. The data sits in remote location. You have some computing power which you can do the rendering, but your workstation is not connected to any of those. So obviously, the one thing you can do, you can transfer all of the data to the visualization center, but that may require quite a bit time depending on the network they have in between. So instead, what you should be doing is you really need to look at what the user wants to visualize, extract that data from the storage, pass that to your rendering servers. Once they actually rendered, then you can get to the client. So basically, the point here is instead of moving the data to computation, you should really move the computation to data. In this case, simple indexing, filtering, and creating the appropriate data structure, move to the where data origin is stored. Then we only move the data that will require for our rendering, and then from there we only move to the client just a single image to display on the computer. So that's the second thing. You need to really pay attention to locality. And the third and the most difficult one is maybe is the take of advantage of parallelism. So I have different types of applications here, and I have one biological application in all three classes that I will describe. I will broadly categorize the applications into three classes. The one of them is what I call bag of task model. So in that case, you have some computation that you need to do that they are independent of each other, but they may depend on some input files. DCMRI was one of the applications we actually use, developed, and that fits into this model. So you have the tasks, and they are dependent on some files, and you can just independently parallelize those to get efficiency. The second set of applications, which I'll call non-streaming workflows in general. So, for example, generating mapping an alignment is one of them. In that case, you have a workflow. So it could be a simple pipeline, or it could be a directed acyclic graph. Part of it, maybe you can do parallel, but you need to do first task, then you can do the second and third task in the second level, and so on and so forth. And the third class of the application is you still have a workflow, but you have multiple data elements that you need, that you can go through that workflow. I'll call them streaming applications. Okay. And each of these applications categories gives you different parallelism. For example, in bag of tasks model, so you can take these tasks and give each of these tasks to different processors. Okay, so obviously if you have more tasks than processors, you can give multiple tasks to one processor. In that case, you again need to pay attention to locality. If you have multiple tasks that using the same set of input files, then you want to put them in the same processor, and you want to make sure that the total execution time is minimized by giving same amount of work to everyone else. So I'll call this as a task parallelism. Okay. The second one is non-streaming workflow. So in that case, let's say that we finished the first phase and first task there, and we are doing the second. We are in the second level. We can actually do those two tasks parallel to each other, and we can also maybe take the advantage of one more level of parallelism, data parallelism, to do one of the heavy tasks that can be parallelized. So we distribute that into multiple processors. We do the data parallelism, and we can do the task parallelism by running two different tasks concurrently on the parallel machine. Okay, and the last one is streaming workflow, which basically give us one more parallelism. Once you finish the very first task, processing of the very first element on by very first task, then you're ready to process, process them in the second level, and you can do that concurrently with new tasks starting, new data elements, sorry, starting from the first task. So you can basically pipeline the execution. That way you can actually really reduce the execution time. Lastly, you can still use data parallelism, you can still use task parallelism. So the important thing for you to look at is your application and figure out which of these types of parallelism is available for your application. Okay, so I'm going to use whole slide histopathology image analysis for neuroblastoma. This is an application that we developed with multiple collaborators, including Dr. Shimada from Los Angeles, and my old friend, good old friend, Dr. Metin Gürkan, who developed the image analysis algorithms. The process basically mimics what a pathologist is doing when they're reviewing the whole slides. So it starts with the lower resolution of the image, and if a simple diagnosis can be done at that level, it's done. If not, then you will go into select some regions, and you will go into higher level resolutions and try to find make the diagnosis based on the image over there. And the workflow for this is given at the bottom. So you have multiple steps starting from color conversion to some statistical features, looking at histograms and classifications. And if you cannot classify, you go back and go one level higher resolution. So it's a busy slide, but the point of this slide is, why do we need to use HPC? We are talking about this size pathology slides. This can be 120,000 by 120,000 pixels, 40 gigabytes of memory. And most of the time, our collaborators develop their algorithms in MATLAB. And if you just look at one small tile of this image, like 1,000 by 1,000 pixels, it will take about 6 seconds in MATLAB. If you convert that into more efficient programming with C, you can get less than a second. But even with that, if even for a small slide and half of the background, it will take about 20 minutes to actually analyze the slide. So what we really want to do, and to make this practical, useful in the clinical setting, we really need to get this under a couple of seconds, because you may really need to look at multiple slides per patient, and basically processing this with just current CPU algorithms will not scale. You will need more than a year to process 1 year worth of data. So how we do that? So first of all, we can chop the big image, the slide, into small tiles. When I say small, maybe 1,000 by 1,000 or 4,000 by 4,000 pixels. On the left side is one slide, and each of those small boxes is one tile. Then we can give this tiles to computational units. We can have multiple computational units, CPUs, GPUs, Intel Xeon 5s, and we want to process them through them and get the classification out of it. So this application actually provides all of those 3 levels of parallelism I mentioned. So first of all, if you look at the workflow, there were different steps, so there were different tasks. So I can do them concurrently, and I can pipeline them as well. What I can also do, I can take advantage of data parallelism. Here, more deeply, this is an application that some of the things that I'm computing fits very well to GPU's scheme of computing, basically single instruction, multiple data. What I'm showing here is, again, too much information in this slide, but just if you look at the top row, there are different tasks in my workflow, and there will list how many input, what size of input and output it's producing. Is it computationally heavy or not? Is there a locality? Is it accessing the same data or not? And all of them have different characteristics. And we have implemented the GPU version of all of those phases. And what we have seen, really, each one of them gives different speed up, right? The speed up with respect to a single CPU core, which I will tell that, that's usually not a good way of representing numbers, but just to be able to compare those 4, having a single baseline is good. Speed up can be from 166 to 8 times. So since your CPU also have multiple cores, you can actually do multiple of them. So if you have a CPU with 8 cores, really doing the histogram computation in GPU doesn't make sense because it's not really giving you a faster execution time. Yet another busy slide. Title recalculation rate means the times that we go the higher resolution. So as that increases, we need to process bigger and bigger tiles. If you just look at the bottom top left chart and the bottom white bars, that's how much the times it takes to how much speed up I get with using GPU only processing. On top of it, I have some workflow optimizations, which includes, how to efficiently use pipelining and overlapping computations and communications, which we don't need to go into detail. As the tile gets bigger, doing it in GPUs obviously gets bigger because you have more data elements to process to do the same computation. So this fits the GPU very well. But one thing I want to highlight at the bottom, if you look at the chart on the right, this is actually the same thing with what we are adding is additional CPU processors. They don't have GPU, so we have a heterogeneous environment. So we are just adding CPUs. So we are adding same number of CPUs. So that means one may expect to get 2 times speed up. We actually get 3 times speed up. So how that possible? It's possible that because we were not efficiently utilizing GPUs. Some of the computations, like processing the smaller tiles, they are really not good for doing those kind of computations in GPU. To get the best out of GPU, you really need to process larger amount of data, and you should be doing the same type of work. So I guess I've run really, really fast. So that wasn't really my intention, but I think I may have more time for more questions, I guess. So I talked about really high-performance computing up until now, and my title says distributed computing, cloud computing. What about cloud computing? So let me just take a few minutes of time and talk about cloud computing. So even though name says cloud, I guess everyone in this talk knows that it's not really in the cloud. It's someone else's computer, right? So it's nice that there are many companies and agencies that are providing us in these as resources, and in many cases these are offered. In case of Amazon and cloud and Microsoft cases, these are offered by companies, and they are models for you rent your computing power instead of buying that computing power, which is great, right? If you don't need the computation 24/7 in your lab, and you have times that you actually need to analyze the data, and you need to just during that time, if you can have access, that's great. And in that case, cloud computing is really helpful. But one thing you really need to pay attention there, you really need to pay for compute, data storage, and transfer, right? So all of these actually comes back to my golden rules that I told you. You're paying for the compute time, so you need to make sure that you're efficiently using computational time so that you're not wasting your computational time. You're going to pay for data storage, of course, however big is your data, but you'll be also paying for the data transfer. So minimizing the data transfer will help you to save money as well. So I don't want to sound negative about it. In contrast, I'm extremely happy that we have this infrastructure. This is actually probably our best bet right now to get sharing of the large data workflows and computational resources between multiple institutions. So after many different iterations of earlier distributed computing, grid computing, standardization efforts, this is actually really one way that we can finally get to share large data and workflows and work together. And also for most of us, not everyone has direct access to the supercomputers. This is really our best bet to get scalability and speed. So because I don't really have time, I cannot go into detail how you can really use this, but everything we discuss really applies to cloud computing as well. If you look at, for example, Amazon today, they offer multiple virtual machines, instances with different number of cores. They even offer with the GPUs, and Microsoft also start offering the instances with the GPUs as well. I will just point you one of the review paper that I used to give as a reading assignment to my students from the Nature Reviews Genetics, even though I don't really agree for everything that's said there. To me, heterogeneous computing is not really much different than cloud computing because it really converge to the same thing. Now cloud computing is giving the heterogeneous computing platforms for us. It's a good review to looking at different applications and how they may also map to some of those resources. What is more entertaining for me was to also read the correspondences following this too. This paper by group Trellis et al. And then the author's response, and they're arguing the suitability of the cloud from different perspectives, which was interesting because both of them were correct in their arguments, but they were not really arguing the same thing. One was talking about transferring 1 petabyte of data to every single node in the 1,000-node cloud environment, which will cost you $6 million at that time. The other was talking about just processing 1 petabyte data in 1,000 processing elements, which will cost just a couple thousand, which is much more manageable. The reason that I'm really highlighting this, when you're talking about different infrastructures and different ways of parallelizing, make sure that you're talking about parallelizing the same application. You're not talking about making the program much larger than what it was doing initially. Make sure that you have the best sequential program in place so that you can actually focus on parallelizing it. So I will end up with a summary. I know I showed you too many things, but I really want to leave this presentation with keeping in mind these three rules and what it can give you. I'm not expecting you to turn all of you to computer scientists, and as last week Trey highlighted, don't try to be jack of all trades. It's not good. The best thing is to find the right collaborator to work with you for the right set of problems. This could be, specialized biologist, or this could be a computer scientist like myself or others. But what I'm hoping that this lecture gave you an overview when you think about your application. What are the places that you need to look for making your application faster, so that, and this will be a starting point discussion with your computer science colleagues. So again, just quickly, the three things is: one, we really need to focus what's the most time consuming, what's the common case, but you also think about, okay, how frequent that is. If it's just 50% of your computation, even if you improve that infinitely, you'll only get 2 times speed up. So don't expect miracles from cloud or parallel computing if you're only improving 50% of your computation. The second is you really need to pay attention to locality. And you need to bring the computation to closer to your CPU when it's possible in single setting, single site environment. But when it's not possible, if the data is really big and you're talking about distributed environment, then you really think about moving computation to data. And the third thing is taking advantage of parallelism. So almost everything we do has many levels of parallelism, including task data and pipeline parallelism. You really need to take advantage of those. Don't forget, again, the fastest processor doesn't mean that your application run fast. You need to make sure that you find the most suitable architecture. So, for example, if you're doing a regular computations like for the image analysis applications we have shown, the GPUs are great for them as long as you process through a big chunk of images. So, and when talking about GPUs or any other architectures, you need to make sure that you have a fair comparison. Comparing a performance of a whole GPU with a single core performance is not a good idea. What you need to be comparing is, if you're comparing a GPU, you really need to compare against what's the comparable current CPU using multi-cores of that CPU. So in regular applications, I've seen that GPUs can be up to 10 times faster in some applications, but in real life, really it's about 3 to 5 times faster, and it's not 100 times faster. But again, it really depends on your application characteristics. So that's actually all I want to cover today, and that's happy to answer.
That's wonderful, Umit. Thank you so much for that really comprehensive overview of high performance and cloud computing and all the factors that go into the decisions for how you begin the process of parallelizing your code and applying it. We have time for a couple of questions. The first question that we have is really sort of a little more practical. Is what sort of rules of thumb or advice could you give to people on kind of when exactly to begin the process of deciding that their code is, could run faster or whatnot, I guess in the context of, could I just improve the performance of my code by writing better code, or do I decide that, oh, okay, my code is as good as I'm going to get it, now I should go and try and improve its speed by going to high performance computing solutions such as,
Thank you very much. This is a fantastic question. So we see this all the time, and I try to allude to this a little bit, but let me expand on that. So when to decide it's time to make your code parallel, the first thing you really need to make sure that you have the fastest sequential code. So your code is most optimal in the sequential setting before going to parallel. If you have a very inefficient sequential code, right, so you can much easily parallelize that, okay? It's much easier to parallelize that in many cases. You can just embarrassingly or what I guess pleasingly parallelize that by partitioning the work. But it is highly possible that there's a better algorithm, there's a faster way of doing that in sequential setting, and that could be still much faster than any parallel example. One example from, I have had multiple examples of this. We had a one parallel algorithm to do one specific task, and we couldn't get a good speed up, but it was a parallel algorithm. Later, another research team came up, and they said they have a framework which it will allow our parallel algorithm to scale wonderfully. So linear speed up. This fascinated me. Of course, this is something I want. But when I look at it carefully, yes, their framework had a good scaling up, but their sequential execution time was 1,000 times slower than my parallel time, my sequential time. So in that case, really wasting more resources is not going to help you. You need to make sure that you have fastest code. But of course, when to stop debugging, and making sure that you have the fastest code, that's a very difficult question. So you need to look at again, maybe 80-20 rule. So if you can really, you don't want to spend 80% of time to make your code 20% faster, right? So you need to look in easy parts that you can make it faster.
That's very sound advice. One other question is, what sort of technologies do you see that are kind of currently emerging or that are on the horizon that will help with minimizing latency of data transfer? So if you are moving data around, you're not kind of hidebound by data transfer rates. Is Internet 2 or whatever, Internet 3, I don't know what's on the horizon. Are those technologies going to be helpful?
There are some technologies, some network technologies will be really helpful in the higher end right now, but I'm afraid we have to deal with low latency in our daily life more often than we are doing right now. And so most of the time, an end user analysis is end up in the workstation, right? And whatever your university or company's network is limited, you will be limited with that. So InfiniBand, for example, is getting much faster network. But if you look at again, even the earlier plots I've showed you, the improvements are usually more in bandwidth than latency. So latency is improving, but it's much slower pace. So you really need to get used to low latency and think about how you can make your algorithm program faster by focusing on throughput and maybe looking at parallelism overlapping so that you gave the illusion of low latency, or basically focusing on memory hierarchy and using it better again to give low latency. So again, the rules I laid out is the best thing to do to achieve better latency.
Fantastic. Well, I'm sorry, everybody who's been writing in questions. We've run out of time this morning, but I want to hope you'll join me in thanking Umit for giving us a wonderful talk this morning on modern computing, cloud distributed, and high performance. Really some great ideas and great heuristics there to use as you're thinking about parallelizing your code. Please join us again next week, next Friday at 9 a.m. Pacific and noon Eastern for another one in our series of the Big Data to Knowledge Guide to the Fundamentals of Data Science. Thank you, everybody. Have a great day.
Thank you very much for everyone for listening.